norms. We say that, for example, norm 2 is equivalent to norm 1 if there exist two numbers, two positive numbers, capital M and small m, n, such that for all x we have these inequalities. Because this definition is symmetric with respect to norm 1 and norm 2, we can say that these two norms are equivalent. Now, for equivalent norms, we have some properties. Lemma 2.13. Let X be a vector space with two norms, with three norms, in fact, with three norms, norm 1, norm 2, norm 3. And let norm 2 be equivalent to norm 1 and norm 3 be equivalent to norm 2. So norm 1 is equivalent to norm 2 because norm 3 is equivalent to both norm 1 and norm 2. So norm 1 and norm 2 are equivalent also. B, norm 3 is equivalent to norm 1 and norm 2. Norm 3 is also equivalent to norm 1. For any norm, we can define a topology. For example, norm 1 introduces topology tau 1, and norm 2 introduces topology norm 2. So when two norms are equivalent, the topologies that they are produces are equal. So norm 1 equal norm 2. 2 1 equals 2 tau 2. Another lemma, let X be a vector space with norm and norm 1. Norm and norm 1 be two norms on X, and D1, D2 be two norms, be two metrics, be the matrices defined by dx and y equals the norm x minus 1 and d1 xy equals norm 1 x minus y. So any norm, you know, introduces a metric. Now suppose that there is a positive k such that the norm x is less than or equals the k norm 1 of x, and for all x in x, let xn be a sequence for all x, and let xn be a sequence in x. So if xn converges to x in metric space x and d1, then the sequence xn converges to x in metric x and d. So if the norm of x is less than or equal k norm 1 of x, we conclude that every sequence converges to x respect to norm d1 must be converges to x in metric d. B if xn is Cauchy in metric space d1, then this sequence is Cauchy also in metric space d. Here we don't suppose that d1 and d are equivalent, because we have just one inequality. For B2 norms equivalent, we should have 3 inequalities as before. Corollary. Let X be a vector space and norm 1 be equivalent. Now we have 3 inequalities. So if norm 1 and norm be equivalent, norms on X, and D and D1 be metric spaces defined by norm and norm 1, like this. Unfortunately, I can't use the electronic pen. I don't know why, but I can use it, unfortunately. Okay. Then for any sequence xn in x a, xn converges to x in the metric space x and d if and only if this sequence converges to x in the metric space x and d1. So if we have just one inequality like this, I show it with a star, norm of x less than or equal to norm 1 of x. In this case, we can say that if xn converges in metric d1, then converges in metric d, not vice versa. But if they are equivalent, a sequence xn converges to x in metric space d if and only if xn converges to x in metric space x and d1. B xn is Cauchy in the metric space x and d if and only if xn is Cauchy in the metric space x and d1. X and d is complete if and only if x and d1 is complete. And this is the proof of the corollary. Important theorem, vector space with norm and E1, E2, En be a basis for X. Now we can define another norm on X by R equivalent. This is very important. In fact, we can prove that in finite dimensional vector space, any two norms are equivalent. This is another corollary. So with this theorem, we can conclude that any two norms are equivalent because the norm here, norm is an arbitrary norm, but norm 1 is a defined norm. So any norm is equivalent to norm 1. So any two norms are equivalent. Corollary. As I said, if two norms, norm and norm 2 are any two norms on a finite dimensional vector space. This is true only for finite dimensional vector spaces, not for any vector spaces. For finite vector spaces, any two norms are equivalent. And the proof is, as I said, from the theorem and the lemma before the theorem. Let me see if everything is okay. Okay. Another lemma, let X be a finite dimensional vector space over field F, and E1, E2, En be a basis for X. If norm 1 from X to R is the norm of X defined by 2, 1, then X is a complete vector space. Norm 1 means this norm. Then we have a basis for a vector space, for a finite vector space. We define norm 1 as this norm. When X equals sigma lambda j ej, the norm of X, norm 1 of X, is defined as the sigma of lambda j power 2, the absolute value of lambda j power 2, or the sigma power 1 over 2. So, lemma 2.18 says that in finite dimensional vector space, norm 1 for a basis like E1, E2, En is complete. So, because all the norms are on a finite dimensional vector space are equivalent, so we conclude that any norm on a finite dimensional vector space is complete. And this is very important. So, for example, Rn, Cn, they are complete vector spaces, complete normal spaces, because they are finite dimensional. Corollary, as I said, if norm is any norm, is any arbitrary norm on a finite dimensional space X, then X is complete with respect to this norm. Another corollary, this is also important. If Y is a finite dimensional subspace of a norm space X, then Y is closed. So any finite dimensional vector space is closed because Y is itself a norm vector space. So this is complete metric space, and every complete metric space is closed. There are some exercises. I will send you the solution of some exercises. Not all the exercises because they are too much. I selected some exercises from any chapter and solved it, and I will send the PDF for you in WhatsApp. Banach spaces. Here we are dealing with Banach spaces, and this is a very important spaces. In fact, a Banach space is a normal space when the metric, as you see, the metric dx and y from the norm is complete. When the metric introduced by the norm is complete, we say that the normal space X is Banach. So Banach space means the norm on the X is complete. I write it here. X and a norm is a Banach space when X and D is complete. For example, L infinity with a small l, that the spaces of all sequences xn, this if we define S as the sequence on in L infinity such that from 1n xn equals 0. So just finite number of xn can be non-zero, and from a number n we have xn equals 0. So this is a linear subspace of L infinity, and we can say that S is Banach space. And S is closed. Oh, it's not closed, sorry. It's not closed. Okay, it's interesting. This is a subspace of L infinity that is not closed, so it's not Banach. I made a mistake, sorry. it's not closed. Okay, for proving that it's not closed, we should find a sequence that converges to a member that is not in S. So, for example, let x equals the sequence 1, 1 over 2, 1 over 3, and etc. Then x is not in S because there is no n that n equals 0 from that n. None of the members of xn is 0. They are non-zero. So x is not in S. S is the set of all sequence xn that from 1n xn equals 0. So this x is not in S, but this is in L infinity. And if we define xn like this, 1 and 1 over 2 until 1 over n and then 0. xn is in S, and the normal x minus xn equals 1 over n plus 1. So the limit of x minus xn equals 0, and it means that the limit of xn equals 0. But x is not in S. X is in the S bar, the closure of S, not in S. So S is not closed, because if S is closed, it must be equal to S bar. So it's not closed. It is interesting. Another lemma: if X is a norm vector space and S is a linear subspace of X, then S bar is a linear subspace of X. So, okay. Okay, your phone is open now, you can speak. I'm waiting for you to hear your voice. Do you want to speak or not? Okay, my voice is okay, but I am waiting for your friend to speak, because he or she, I don't know, asked for phone to speak, and I accepted. Okay. So I continue. What does it mean? The closure of S or S bar is a linear subspace. It means that for any two member X and Y in S bar and any scalar alpha in field F, we should prove that alpha x plus y must be in S bar. For proving this, we say that because x and y is in S bar, there are sequences xn and yn in S such that x equals the limit of xn and y equals the limit of yn. This is true for any member of S bar. So, because S is a linear subspace, the x1 plus y1 is in S for any n. So the limit of xn plus yn equals x plus y must be in S bar. Any sequence in S converges to a member of S bar. So because xn plus yn is in S, the limit of xn plus yn, that is x plus y, must be in S bar. So we prove that for any two member x and y in S bar, the addition of these two members is in S bar 2. And for any alpha xn is in S, because S is a linear subspace of x. So alpha xn for all n x in S. Again, we can say that the limit of alpha xn, that is alpha x, must be in Sn. So any linear combination of two members of Sn, S bar, is in S bar. So S bar must be a linear subspace. Unfortunately, internet doesn't work normally, and we should wait. Okay, we should wait until the problem solved. Okay, now you can continue. Oh no. Definition. Let X be a norm vector space and E be any non-empty subset of X. As you see, E is a subset of X. We say SPE. SPE means the smallest subspace of X that have E. So let E be a non-empty subset of X. The closed linear span of E. Closed linear span of E. We show that by SPE bar is the intersection of all closed linear subspace of X which contain E. So SP of E equals the intersection of all linear subspace of X that contain E, but SPE bar equals the intersection of all closed, F here is closed in SP bar, is closed linear subspace of X that contain E. Now we can show that SP bar equals SP bar. It means that lemma let X be a norm space and E be any non-empty subset of X. SP bar, when bar is on just SP, is a closed linear subspace of X which contain E. And SP bar E equals SPE bar. Here bar is on all SPE. That is, SPE bar is the closure of SPE, as you see. Another theorem or is lemma. Suppose that X is a norm vector space and Y is a closed linear subspace of X. So we have two linear spaces. One is X and another is a subspace of X. And Y is closed. If Y is not equal 0 and alpha is a real number between 0 and 1, as you see, then there exists a member X alpha such that the norm of X alpha equals 1. So X alpha is a unital member, is unital, and the norm of X alpha minus Y is greater than alpha for any Y in Y. So X alpha from the linear subspace Y has at least alpha distant. This is the proof, and I said for a study. When I said for a study means I doesn't want the proof in the final or mean exam, It's just for your study. Another theorem: if X is an infinite dimensional normal space, here X is not finite dimensional, is an infinite dimensional. So the dimension of X, as you see, equals in infinity. And D equals all X that the norm of X is less than or equal 1. This is the closed unital disk. And K is the set of all X in X such that the norm of X equals 1. The theorem says that neither D nor K is compact. So none of D and K is compact. They are not compact in infinite dimensional normal space, but they are compact in finite dimensional normal space because they are closed, and so they are complete. But in infinite dimensional normal space, they are not compact. The proof is for your study. Definition. Now we are going to define Banach space. A Banach space is a normal vector space which is complete under the metric associated with the norm. So if the norm is complete, it means that the metric associated with the norm is complete. We say that X is a Banach space. So Banach space is a complete norm space. We said that any finite dimensional vector space is complete. The norm, any norm finite dimensional vector space is complete. So any finite dimensional normal space is Banach space. For example, C power n, R power n, MNR, and NC means the all matrices, square matrices of order n with entries in R or entries in C. All of these spaces are Banach space. Another example of Banach space are, for example, CFX and LPX for P from 1 to infinity when X and sigma and mu is a measure space. Capital LP means the measurable function from X to C, that the integral of absolute value of P of F power P is finite. Here this theorem says that capital LPX is Banach space, and also a small LP. small LP consists of sequence in C with the norm that with norm LP, that the norm of this sequence must be finite. Another another example of Banach space: if X is Banach space and Y is a linear subspace of X, that is if Y is a linear subspace of X, then Y is a Banach space if and only if Y is closed. So any closed subspace of a Banach space is also a Banach space. We should wait until the problem, okay. Okay. Definition: let X be a normal space and Xk be a sequence in X. For any positive integer n, let Sn be the sigma xk from 1 to n. Sn is the nth partial sum of sequence. So Xn is the addition of x1 until xn, the nth partial sum of the sequence. The series xk is said to be converges. This set is said to converge if the sequence Sn, the linked up sequence Sn, exists in X, and we define the series xk, k from 1 to infinity, as the linked up Sn. So for defining the series, we say that a series xk is converges when the sequence of the nth partial of sum of the sequence has a limit. Now we have this theorem: let X be a Banach space and Xn be a sequence in X. If the series of the norm xk converges, then the series of xk converges also. We say that the series of norm xk converges. If this series is converges, we say that the series xk is absolutely converges. Here this is a real valued series, but this series is a series in Banach space X. The proof is for your study, and now we have some exercises. I will send the solution of selected exercises to you later, inshallah. I think this is enough for today. Next session we will start inner product spaces and Hilbert spaces. So it is enough for today. And I should say that the next session will be at next Sunday. This week we have just this session, not two sessions. So we won't have a session at Tuesday. The next session will be at Sunday, remember. And the next week we will have two sessions. One at Sunday and the other at Tuesday. Okay, any question? So the next session will be at, the next lecture will be at next Sunday. Okay.